All right. Good afternoon, everyone. Today, I want, much like the most well-known question, what happens when you type google.com into the browser and you hit enter? I wanted to do a similar thing for cargo. And so today, we're going to ask the question, what happens when you run cargo build? So a little bit about who I am. I'm a senior software engineer at InfluxData. I currently work on the 3.0 open source and our pro version of our database. And I've been a Rust user since 1.0 released. And I think build systems are pretty awesome. And today I want to talk to you about one near and dear to my heart, cargo. So what are you going to learn today? We're going to learn how cargo chooses the correct version of Rust C. We're going to learn how cargo compiles a zero dependency program, like your bare bones. I just started my cargo new. We're going to learn how cargo compiles a program with dependencies, and we're going to learn how those dependencies and the versions are actually chosen. So this is a high-level dive into the concepts of how cargo works. We're not going to look at like cargo code specifically, and we only have 25 minutes, so I'm going to have to gloss over some things, but hopefully you'll be able to get the nitty-gritty, important details of how cargo works. So let's do a little basic overview of cargo. For many people, this is your interaction with cargo. You type build, you hit enter, you get a binary, or the borrow checker yells at you. But that's not actually what's really happening. It looks a little something more like this. You're typing enter, you're hitting build, it's resolving dependencies, it's doing all these different things, and there's a lot of things that cargo is doing under the hood in order to make sure that you can actually get that binary. And there's a lot of ways that can actually fail. And so we're going to talk a little bit more about that happy path of everything working. So the question is, which cargo are you actually running? You know, if I type in which cargo into my shell, you can see, oh, hey, there's cargo in cargo bin/cargo, my home directory. But I think we all know that if you use rustup, you can choose which version of Rust you want to use, 1.7.9 or 7.9 or 1.80. So where are all those versions of cargo? Well, with a little help of FD, we can see that they're actually all in .rustup/toolchain. So you can see on my machine, I had 1.77, nightly, stable is on here. So we have this cargo that's on our path. We have the missing cargo, which is our cargo bin that we originally saw. So which one is actually running? Well, here's the secret. It's not actually cargo. It's rustup. And in fact, it's not the only Rust program that's like this. So if we look into our cargo bin directory and we say, hey, show me all the files with links greater than 1 and show me the inodes, you can see that they all have the same exact inode, which means they're all the same file. They're all pointing to the same thing. So all 14 programs that you have when you install them with rustup are all just rustup. They are just hard links to it. And so it looks a little something like this. So what's actually really going on when you hit enter? Cargo is found on your path. This cargo is run, but it's actually rustup. And rustup looks at the 0th arg that gets passed in. So anytime you invoke a program, like say you did cargo build, or you ran like, I don't know, Chromium or something like that. That 0th arg that always gets passed into the program that you can like parse out from your arguments is the name of the program itself that it was invoked with. And so this trick here is that by saying that the file name was cargo, but we're passing, it's actually pointing to rustup, rustup can go, oh, I need to run cargo. And so it checks for, you know, which version of Rust that you're using. So it'll check your rusttoolchain.toml file, or it's going to choose your default. So if you specify stable when you install with rustup, that's usually what you're ending up using. And then it downloads that version of cargo into .rustup toolchains if it doesn't exist. So this is where the magic happens. You know, you change the version in your Rust toolchain file every 6 weeks. You run cargo build, and it just downloads it for you. It's rustup, actually. And so this isn't the only programs that done this. This is a trick that has been used in Unix for many years. And if you're interested in learning a bit more about other types of shenanigans like this, the Axo dev people wrote a really good blog post about this called An App by Any Other Name. And the slides are in the Discord, so that's a clickable link if you wanted to like go that. You don't have to write it down. So Let's build a binary or a library with 0 dependencies, the most bare bones, simple example that we can do. So this is kind of how it works. Cargo gets invoked, it sets up logging, parses any flags that are passed to it. This is the cargo that we are meaning to actually run this time, not rustup. We determine which subcommand to run. In our case, we're using build, and it passes any needed context to that command. So the other thing is that we acquire a lock as well. So if you've ever saved in Rust Analyzer in your editor, and that's running, and then you try to run cargo build immediately after, and it says, hey, it's waiting on the lock, that's what's happening. It's been about 70+ years, and the best way that we communicate between two programs is putting a file in the file system saying, hold on, I'm doing something here. Please don't touch this, and then deleting it later. So after that lock is acquired, we generate a plan to build a package, but since it's just one program, it's a very simple build plan. There's no dependencies, no proc macros, no build scripts, none of that. And then it actually executes that plan. So let's see that plan in action. OK, sorry. Normally I had to click through here. So what happens is that we have the we are going to create a cargo new bin. We are going to cd into that, and then we are going to cargo build-v. Cargo build-v is the verbose version of cargo build. And we can see that we have here in our crate name that the example binary is created here. And edition 2021 is passed in. Edition, remember this, is that edition was added in 2018. So when you're compiling with rustc on its own, it defaults to the 2015 edition, because you would break a whole bunch of scripts, possibly, if you had passed in, if an edition defaulted to, say, 2021. And so we have to specify, oh, we are using edition 2021, and this is done in our cargo.toml file. But rustc defaults to 2015. And the other important bit here is that our out directory is target debug deps. This target directory is a convention created by cargo. There is no specific place to put output files. There is no specific way that you have to do all of this. But cargo has created a convention that all of us follow, and that's where we decide to put everything. And the same goes for source/main.rs or source/lib.rs. These are all conventions that cargo has created. rustc doesn't particularly care about where you put the files. It will compile things. But cargo cares where you put those files. And because we have all standardized on here's how it is, we're not fighting about project layouts or this should go in this file folder or that should go in this folder. No, cargo has chosen for us, and that is what we all do, and we can spend our time doing a bunch of other things. So if we see this, if we look at the target directory, we can see that in the debug, we have the example bin. It gets output here, and so when you run cargo run, for instance, it'll build the binary, dump it out into this directory, and then actually run that once it's completed. So let's build a binary or a library with one or more dependencies. So just like before, it's pretty much the same. Cargo invokes the logging, parses any flags that are needed to it. It determines which subcommand to run. We know that it's going to be build. It gets the lock. And this time it generates a plan. So it's going to resolve the dependency graph. So, you say that you have 5 dependencies. It then goes, OK, know that you have these 5 dependencies. What are their dependencies? And then what are those dependencies? And it keeps going through until it creates a graph of, I have a dependency that has no dependencies. And that is your dependency root. And so once it's resolved the dependency graph, figured out which versions of all these things to use, it'll try to download those packages if you haven't already downloaded them in a different Rust build. And it starts from the roots, compiles those packages in that build graph in a way towards actually building your binary, and it tries to do that as parallelized as possible. And then it will compile the main binary or library by linking the dependencies into it. So it creates all of this plan, creates a bunch of jobs, and then it spawns it onto a make-compatible job server. which also means that Cargo can work inside of make scripts as well, which is kind of a neat little thing. And then it actually executes those plans by pulling things off the job server to do. So let's talk a little bit about package versioning. We're going to do a little quick primer here. Here we have packages B and C. They're both at versions 1.0, and we have package A at 1.0. In this case, B and C are our roots because they have no dependencies, and A is our final binary. So we can compile B and C in parallel. When we're done compiling them, we can link it into A, and then we can compile it all. Everyone's happy. This is the happy path. Everyone is having a good time. So let's add another dependency. B and C now depend on D at version 1.0. D is now our root. We compile D, and then we can compile B and C in parallel because all of their dependencies have been built, and then we can compile A. So notably, B and C here are using the same version of D. So what happens if they don't use the same version? Well, we have a couple different options available to us. In the case of Rust and Cargo, it will try to compile both of them. So if they are completely incompatible versions, like in this case, we have 2.0 and 1.0, it'll go, OK, I will just compile both of them and link them in, and we are going to take the hit. Sorry, we had to do that. It's better to have a running compiling program than nothing at all. But other build systems decide, hey, no. We only want one and only one version of every single package. Haskell's build system Cabal does this, and I can tell you from when I was a junior programmer, it was never fun when Haskell got an upgrade. It was a hard time in order to get all those dependencies working all together at the same time. So Cargo makes a reasonable trade-off where you might have a little bit of a bigger binary size, but hey, at least you got something that compiles. Now, let's say that D was at version 1.5.0 for B. And we said for C, I'll take 1.5.x. In this case, Cargo can go, oh, well, C will choose any version as long as it's 1.5 something, and B only expects 1.5.0, so we'll just use that version. And that's kind of how it links. So its algorithm is trying to figure out, OK, given all the requirements, how can I try to minimize the amount of times I'm compiling two versions of the same package? But semver is hard. Cargo tries its best, and sometimes people will also do the semver trick wrong, and now your crates don't compile. It just happens. But Cargo does its best to make sure that everything works the way that we expect it to. There is kind of an exception to this, though, is like if you have dependencies put into the public interface. One example from work is that we have our object store crate to interact with like S3 and everything like that, and we have this object store trait. And if we don't keep all of our dependencies in lockstep versioning using the same version of object store, and we have something in the public interface, which version of the trait do you use? Right? You can't have both in the public interface and compile two versions of the same crate. So that's kind of the only exception to it. Otherwise, it can compile both versions of the crate, and you have a good time. Otherwise, Cargo spits out an error, and it's a little bit verbose, but it's somewhat easy to fix. So let's actually take a look at what Cargo build is doing then here. Again, it's going to look at your cargo.toml for your crates, your dependencies, and then kind of go through and create that graph and try to figure it out. And if it's done it before, it's in your cargo.log file, which is also just a toml file. So if you ever kind of wondered like what my dependencies are in my entire dependency tree, you can just kind of like look at that and grep through it. And so as it goes through, it updates the registry. Maybe there's more metadata, which contains the metadata about all the packages on crates.io, their versions, their dependencies, and it tries to recursively figure out all the crates that it needs. And so if you care about like what the actual algorithm to do it is, it's here at the docs.rs link here. But it figures out which versions, and it's an NP hard problem, so it just tries to do a like best effort kind of thing. There's a lot of research that goes into like how do I choose the correct versions. And so if you're doing cargo upgrade, it'll update the cargo.lock. But if it hasn't created a cargo.lock before, this is your first time invoking the program, it will actually create your cargo.lock file containing basically all of this information. So then it downloads all the crates that it actually needs. It compiles the deps, starting from the roots like we talked about before, and then it compiles your final library. So let's take a look about seeing it in action. So here we're going to add our the clap crate with the derive feature. And you can see that we've added it in. And now we're going to actually just run cargo build without the -v. You might notice that there's sync crate has been added here, but I have a bunch of things that are compiling here that are not the sync crate. So where are the other downloads? Well, there's a basic, and we'll kind of see a little bit later, but there is a registry package cache under .cargo in your home directory that contains all of the crates that you've ever compiled for any Rust project on your machine. And this is nice because then you're not downloading these crates per project. You have a singular place to store them all, save some space on your disk. We all know that Cargo already takes up like 32 gigabytes just to build something. So it's nice to like take up a little bit less space. So in this case, it was like, oh, the only thing that you haven't downloaded was Sin at this version, so I'm going to download it for you, compile everything. So let's take a look at it with the verbose flag. As you can see here, it's running rustc on the stable version. It's chosen it as we expected. This time it's with the crate name clap, and the edition again is 2021 because that was what was in the clap crates cargo.toml. And you might notice that you can see .cargo/registry/source/index crates, clap at that version, source lib. That whole long string is where that particular crate is located. So it's not compiling it inside of your Rust project. It's choosing the source code in another place in another directory. An interesting bit here is if you'll see this --config feature equals derive bit. Feature equals is just a cargo convention. Config is a rustc specific thing. So you can kind of config out whatever. And if you were compiling with rustc, you could put whatever you wanted in the config blocks. But the feature equals as a standardized thing is more of kind of a cargo convention. Maybe they'll add different things that we can config. Who knows? And you'll also notice that we are using a crate type lib. So it is going to create a Rust specific library file, which is a .rlib file. And this -l feature is that it's pointing to, we want the output for any libraries that we might want to use for this. So we've already compiled all the stuff up to now for clap. Any libraries you might need are in that target debug deps folder. So pretty much any build artifacts that we build for any single dependency goes there. So let's take a look at it again, but this time with our rustc binary. You can see again, we are running it with rustc on stable. Our crate name is example bin, edition is 2021. The outdir is once again in the same place. And we are saying our dependencies are in target debug deps. And the interesting bit here is that this --extern, this is how we signal to the Rust compiler, hey, this library that I need, this extern dependency, is available in this directory. And it used to be, in 2015 edition, you'd had to put like extern crate clap. This kind of dealt with that for you to let the compiler know, oh, that clap is an external crate. So if we peek into our target directory, you can see that pretty much all the things in the deps folder are the binary that we made, as well as every single Rust library that we have as well for all the dependencies. And if you notice, there's one singular shared object file for libclap derive. That's going to be your proc macro. We're not going to go too much into it today, but basically it'll dynamically get loaded up into rustc to do all the token expansion, which is pretty cool. So what did I leave out with cargo build? Quite a lot, actually. The registry, how it works, running and compiling tests, build scripts, proc macros, incremental builds. There's so many different things that Cargo is dealing with and doing for you. And it's created this standardized convention for us about how we should lay out our projects. I think if you want to learn more, it's worth browsing through the source code, making and compiling those examples yourself, especially if you want to see, like, how does a build script work? How does the proc macro work? You can find all the code for Cargo online here at this link. I think it's really, really well documented, probably some of the best documented code. It is well worth the time reading it just to get a feel for how they do things. And they also have the docs available on docs.rs because you can also, if you didn't know this, use Cargo as a library directly in your Rust code. So it's not just a binary. So in conclusion, I wanted to just talk to you a little bit today, just walk you through how Cargo build works. I think Cargo is an amazing tool. I think one of Rust's superpowers has been its tooling from the get-go. Like, I don't think Rust would have the adoption it has today if it was not for the tooling. And Cargo, RustDoc, Rust format, all these tools that have been around since like the early years and some a little bit later have really made it easy for anyone to be a Rust developer. You go from one project to another, you're not figuring out how their build system works. You're not figuring out how to format their code. You're not figuring out all these different things that might be different on a project-to-project basis. You just run in, you hit Cargo build, and then you're there. So I want to thank you all for having me here today. I hope you learned a little bit about Cargo. If you want to contact me, you can see me up there. And I will be available after the talk and also on the Discord. So thank you for all your time.